Hi class, today we're going to be discussing Lewis structures and how to put these Lewis structures together in a compound. So Lewis structures for molecules. We already covered how to draw elements with their valence electrons around as dots. Now we're going to start to put these together in a compound. We need to do this because we need to look at how these compounds are oriented. This has a lot to do with how reactive they are, how they react in chemical reactions, their properties, so forth. Everything about chemistry and how we know it is based on how these are set up in their molecular models. Water is a perfect example, and I'll get to that as we start expanding on this. When we start looking at this section, when we get here, water will make a lot of sense, that the chemistry behind it. But we're going to start out simple. So a molecule is represented by a Lewis structure. Lewis structure has the valence electrons around it, and we can use a dash or a line to clean it up. So you see how here we have all dots, but when you clean it up with dashes, it looks a lot cleaner. You can see it easier. You can see what's around it easier. So we draw things like this. Also, after an hour of doing these, this gets tiring. So it gets really sloppy as well. So we're going to start drawing our molecules like this, but you need to understand that 2 electrons equal a dash, which is a bond. It is a covalent bond of electrons being shared between those 2 elements. Now, so I've covered this. Okay, so let's go on to the next page. A hydrogen, we're going to start out simple. A hydrogen has 1 electron. If you have 2 hydrogens that are close by, they both have 1 electron, but both can take another electron to fill the noble duet of helium, the noble gas. As these hydrogens get closer together, they actually want to come together. They are attracted to each other. They will form H2, which is a gas. Hydrogen gas is found as it's called a diatomic molecule, and I'll cover that later. It means that it's not found by itself. So you're not going to find hydrogen by itself with 1 electron, 1 proton. And if you look at the Lewis structure down here, it's not going to be found like that. It's actually, in nature, it's found as a gas like this. It has 2 electrons. It has 2 hydrogens. We use a dash. It is found with 2 hydrogens attached. It is in its normal state, and it's actually in a stable environment like this. This is not stable. But they share these electrons, and this produces the hydrogen gas that we know. Why do these come together? They come together because actually far apart, they are very high in energy and they're not stable. Everything about chemistry has to do with stability. Everything will always try to find its most stable form. And it will always be the lowest in energy. So something that's high in energy does not last long. It doesn't last long because it's looking to form attachments. It's looking to do something in order to get out of this high energy that is up here. So as these get closer, it will pull them together and it will become hydrogen gas, which is the hydrogen molecule here that we see. This is lower in energy than what is up here. So these actually will come together and form this, and it will be in its stable, lowest energy. This is what some reactions, this is not necessarily reaction, because nothing's changed with it, but it is coming together to form its more natural, stable state. So now let's take a look at ammonia. Ammonia is represented with a nitrogen and 3 hydrogens. Now the dashes here mean bonded pairs. These are actually 2 electrons here, 2 electrons here, 2 electrons here. You haven't seen this part before. This is a lone pair of electrons. Nothing's bonded to them. And this is meant to be this way. This is actually stable like this. Certain compounds can take lone pairs on them, which is usually nitrogen, oxygen, sulfur, phosphorus. Right now, we'll tend to focus on oxygen and nitrogen more than the rest of them. Now, I want to point out a few things. Writing out the compound does not show you at all how this connects to each other or that there's a lone pair. You'll just have to write this out. You would have to figure out nitrogen's valence electrons, hydrogen's valence electrons, and then visually draw them coming together. And you'll have a lone pair that is not attached to anything. You cannot create a double bond with hydrogen. Hydrogen is filled with 2 electrons. So this will have to have a lone pair on it. And as we start going through, you'll now see that some of these compounds that we've been looking at actually have lone pairs that we haven't drawn out. The thing is, in chemistry, sometimes they draw them out, sometimes they don't. Just because they don't doesn't mean they don't exist. You just don't see them. You would have to count the octet. So 2, 4, 6. And if these were missing, then you would have to just know that there's a lone pair on here, because there would never be 6 and call this stable. It has to fill an octet. So here's fluorine. Fluorine is also a gas. It is in 2, just like hydrogen. It's a diatomic molecule, and the same rules apply. It has an opening to take on another electron. 2 fluorines come together. They are lower in energy, and that is how they are found in its natural state. So the term is electron dot formula, and so either Lewis structure, electron dot formula would be used. You need to understand the terminology to know that that's what's being asked of you. So again, you start out with them separate, draw them separate. If this is a hard thing for you to visualize, I would suggest you buy, or if you have a child that has little toys, that are similar, or beans. Beans are a good thing to like put around an object, and then you can move them together and start visualizing what is being created here. Because sometimes drawing it just doesn't give the same effect as if you're physically trying to put these and move them around so you can see what's going on. So they start out separate. You bring them together, and if you count 2, 4, 6, 8, 2, 4, 6, 8, these both have octets around it. And the electrons that are shared, we draw a bond, and then these have lone pairs. So the covalent bond is here, and each fluorine has 3 pairs of lone pairs. Again, the lone pairs might be drawn, they might not be drawn, but you have to know that they're there. And then F2 gives you no indication that there's lone pairs around this. And this is what the fluorine molecule would look like. There are 7 elements that do not exist by themselves. They exist as what we call diatomic, di meaning 2. They are 2 molecules attached together. This is how they exist. Most of these are gases, and they are stable like this. Oxygen is O2. We should know that very well. In nature, it's found with 2 oxygen molecules combined together: nitrogen, hydrogen, fluorine, chlorine, bromine, and iodine. As they go down, iodine is a solid, but will start having vapors and so forth. Bromine's a liquid, I believe. Right off the top of my head, I can't remember, but I'm almost positive it is. And but you see, it kind of looks like a 7 here on the periodic table. And then across, you look at hydrogen. These are found combined together in nature. And it makes it easier for you to understand that these are a gas. This is what it looks like for fluorine. If we go back to hydrogen, that's what hydrogen looks like. It has 2 together, and it would either be like this, or we tend to draw it like this more than anything. Okay, so sharing electrons between atoms of different elements. The number of electrons a nonmetal shares and the number of covalent bonds it forms are usually equal to the number of electrons it needs. This is not always the case, and you'll find that out later. But for now, this is how we're going to learn this. So what it means is that if you look at group 1, hydrogen is listed in group 1. It has 1 bond. Boron is in 3A. It has 3 bonds. And does not meet octets, and I'll cover that right now. 4A has 4 bonds for carbon, and silicon has 4 bonds. Okay, now nitrogen, so what this is saying is in order to make an octet. So here we start looking at it the other way. Nitrogen is 5A. You need 3 electrons in order for this to fill an octet. That means that the difference between 8 minus 5 is 3. These usually have 3 bonds. Oxygen is 8 minus 6, needs 2 bonds, 2 valence electrons to fill an octet, has 2 bonds going down this group. 8 minus 7 is 1, and these usually have 1 bond. So look at what needs to be 8. So 8 minus 5, 3 down this group, 8 minus 6, 2 down this group, and 8 minus 7 equals 1 down this group. Okay, so you can see that this is how many bonds we're going to start out with here. Now, again, not everything's set in stone, and there are always exceptions in chemistry, unfortunately. We'll cover those later. So drawing a Lewis structure. So first you start out drawing the Lewis structure of the elements alone. Then you draw them together. And this is not as clean and clear to understand as this. But all of these should have a duet, which they do. And this is 2, 4, 6, 8, has an octet. A dash equals 2 electrons. The central atom, hydrogens are never central atoms. They are always bookends. They can't handle an octet around it. Carbon has 4 valence electrons because it's in group 4. It needs 4 more. It will be the center atom. Usually, when you're dealing with molecules, the central atom is the one that's by itself. And I'll show that as we get to it. There is actually more rules to it, but I don't want to overload you with some of this stuff. So here's electron dot formulas. Make sure you understand that. If it's being asked of you, you should understand the terminology, not just how to jump in and do problems. So carbon, there's only one carbon, so carbon would be central. Hydrogens are never in the center. Same here. Nitrogen is in the center. It has 3 bonds because remember it's a group 5 and it has 1 lone pair. And here we have oxygen. Oxygen is in group 6. It needs 2 electrons, so that means 2 bonds, and it has 2 lone pair on it. And all of these feel octets as well as duets. Okay, so let's practice drawing some of these. So we have phosphorus trichloride, and we want to draw this out. So the first thing you're going to need to do is draw it out of the elements. Don't worry about the molecule, the electrons right now. Phosphorus is by itself. Molecules tend to be very symmetrical. They are lower in energy like that. So P would be the center. None of the chlorines would be, because how do you know which chlorine to pick? So phosphorus is in the middle. We draw it kind of like a triangle around it. And now we got to determine how many electrons are in total here. Phosphorus is in group 5. So we have 1 times 5. We have 5 there. Chlorine has 7 and we have 3 of them. So that's 21. So we have a total of 26 electrons that have to be filled here. This instantly tells me that I'm going to have lone pairs on the chlorines because we only need an octet to be around phosphorus. So we've got to put those rest of those electrons somewhere, and they have to be a part of the molecule. You can't just leave them off. So here we draw lines. So we have used 6 out of the 26 electrons. So 2, 4, 6. Now we just spread them out between all of these. But the first thing you should notice is this needs more electrons because phosphorus does not have an octet. So the first thing I would do is fill in 2 dots there. That now becomes 28. So now let me count. 30, 32, 34. Oh, did I mess this up? Sorry. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. I have used all 26 electrons and I am showing the lone pairs. Sometimes this will be asked. If you're using electrons, you're going to have to show that you used all electrons around a molecule. You can't just leave them off. It'll show incomplete and that you did not finish it. And you knowing that there's 26 and showing it are 2 different things. You have to show that you understand it if that's what the assignment's being asked for. Okay, so now we get to double and triple bonds. What happens in some cases is that there's not enough electrons to go around every element. So we start shifting electrons around. We move them around, and some molecules can handle this. Carbon, oxygen, nitrogen tend to be the 3, phosphorus, sulfur. But carbon, oxygen, nitrogen tend to be the 3 that we'll look at the most. We can move electrons around, and this creates double and triple bonds. And in this way, they all meet the octet still. So here we have 2, 4, and that's 2, 4 here. And we have 2, 4, and we have 2, 4 here. So if we count the octet here, it still manages to be for every element. 2, 4, 6, 8. And that's for oxygen, 2, 4, 6, 8 for carbon, and 2, 4, 6, 8 for oxygen. Carbon's by itself, so it would go in the center and surround itself by oxygen. It makes it very symmetrical looking. Now, triple bond, same rules apply. Hydrogen can only have 1 bond. It will never have more than 1. So if anything's going to happen, it's got to be between the carbon and nitrogen. So if anything on either of these is deficient, then we move and we create a triple bond, which you can see here, 2, 4, 6. This is 2, 4, 6. So both of these have 6 within them. This one now has 8 because of the hydrogen carbon bond, and this one has a lone pair on it, and that creates 8. There are exceptions to the rules. I'm not going to really focus on the exceptions right now. I would rather have you focus on learning how to actually put these together. I just caught another error. This should not be a space in here. This should be bromine. But there are exceptions. The biggest one that you would need to know is boron. Boron is in group 3, which means it can have 6 electrons and not 8. And it's very stable like that. It does not want more. And this is because of where it's located on the periodic table. It's in between metalloids and metals. And so it's got characteristics of some and characteristics of another. And we're just going to leave it at that for now. So it is very stable, not having 8 electrons around it. And sulfur, as you can see, has way more than 8 electrons around it. It can have bonds 2, 4, 6, 8, 10, 12. It can have 12 electrons around it. This gets into more chemistry. At this moment, we're not going to really focus on it right now. We'll come back to this, okay?